Right, great. Good morning, everyone. Today is my last lecture. On Monday, I introduced this paradigm of combining machine learning with static analysis. That mostly means model check, because it certainly means a model checker if the object that you're learning is a state machine. So combining learning algorithms for models of computation with static analyzers, doing that in an iterative way, so building a model up gradually over time and repeatedly analyzing it with a static checker, and then trying to find counterexamples, check if they're true or false negatives, and then returning to the user. So that is an iterative approach that automates requirements testing. It's a black box approach. It can be pretty damn fast. You can do a lot of things to optimize it and make it faster, so that I would say at the moment we don't know where the outer limits of this technique are, but we push them back every year. We'll see that a little bit today. Yesterday I talked about the Lstar algorithm, Angloin's famous Lstar algorithm. It is absolutely the best known algorithm, I think, probably because it is very pedagogical, easy to understand, easy to implement. If you're interested in these kinds of algorithms, I think I mentioned yesterday, there's a library of open source algorithms called LearnLib that one can go out and use. To tidy up some details, I think I should have mentioned it. I think I did, but I should come back to it. In Lstar, you will do automata learning with something called the reset assumption, which is to say that you have this black box, and you assume that with this black box, you stimulate it with it by firing in an input string, okay, and observing the output string. But you assume that there's, by some mechanism or other, you can return the system back to the same known state again and again and again, okay? And this is quite important. There are automata learning algorithms that don't do that, so they abandon the reset assumption, and instead one learns with as little as one really very long string, okay, arbitrarily long. So you just drive the system over time. That's another paradigm of automata learning. You can read more about both paradigms in our book that's coming out, the LNCS 1102. Did I say 5 or 6? I think I might have said 6. I'll check that at the end, yeah. So you can read about those kind of things there. Right. What we saw on Monday was very much unit testing. So basically, you know, somebody comes along, they give you, say, an automotive ECU, they tell you what the API is. They can make it really black box. So when we work with industry, they won't give us the C code because it's proprietary, okay? This is an issue for industry in general, that people are very protective of IPRs. So they give you a DLL, they tell you you're not allowed to reverse engineer it, so it's really black, okay, in a strong way. And then, you know, you stimulate this, you reverse engineer the model, you evaluate the model, you try to find out what the requirements are by talking to engineers, and you basically automatically test that, and you can get nice results. So that is okay. When you look at Lstar, I think it's really quite difficult to say, you know, what can you do with this algorithm? What real-world problems can you solve? So that's what I want to address today, and is very much in the area of cyber-physical systems. Just for historical reasons, I've worked more with the automotive industry than any other in the last 10 years. And it's been a productive collaboration. We went into this project here, SafeCOP, Safe Cooperating Cyber-Physical Systems, which is, I think, a 28-partner consortium. Melodon's Hug School is there, Elizabeth is there working hard on the wireless part. So cooperating cyber-physical systems using wireless communication, so that includes things like, you know, hospital beds that have to be moved around, they're not allowed to hit patients or each other, and they can tell each other where they are. A platoon is the obvious example that we're going to look at here. You can make a platoon out of submersibles out in the ocean. So things which have a degree of autonomy but talk to collaborate and achieve a goal. Drones one could add to the list, okay? So the project is to study such things, and we have looked, I've formed a collaboration with Camcom, which is a telecom company, and here we've been looking at a distributed algorithm to achieve emergency braking in a platoon. So the platoon is going, typically, the platoon is going along on the highway, a child steps out, the lead driver sees this, pulls the handle, and everybody has to brake as effectively as they can, okay, and signal to each other what the heck they're doing to, you know, optimize to give the child the greatest chance to live, and the truck drivers too, okay? So, so they posed us the question of evaluating this algorithm, and evaluating this algorithm, because it's distributed across all the vehicles in the platoon, you cannot evaluate bits of it in isolation, okay? This is a real system of systems. And we talk about black box testing, and we throw the black box around an ECU, which is a small physical object, right? Here we're throwing the black box around the entire platoon, okay? So we put in a very large piece of software, but it is at the end of the day just one piece of software running in a simulator. We're also going to run these things in simulations for the obvious safety reasons, that we're looking for crashes, and you don't want to do that on the road. And in general, this approach of virtualizing safety analysis and simulation is one that's, it's always been popular, but I think it's simply become more popular with you know, the recent crashes that we've seen in autonomous systems. So this is quite a powerful way to go. It's a very productive way to go, because if you have simulators, it's much quicker to clone a simulation than it is to physically clone another mechanical truck, right? It costs you a hell of a lot less. In fact, it costs you nothing if your license is, you know, if you have a site license. So we're going to look at, you know, evaluating the safety of a distributed algorithm inside an entire platoon. And what we're going to do is we're simply going to stimulate the lead driver behavior. Okay, so those are our in signals. That's the main in signals. Here's the architecture I was talking about, just to remind you. So we have a system under test. So this system will be an entire vehicle simulator now, okay? And the learning algorithm will be firing in test cases, and the test case here will be a sequence of driver actions. And the driver actions, mainly we've looked at a 1D simulation where the driver actions are just accelerator and brake, okay, of varying strengths. Of course, in 2D there would be the steering angle, but we've not looked at steering angles so far. I think that's just on the horizon now. So that's the setup. If you run this thing on a single core, it's pretty damn slow. If you think back to Lstar yesterday, Lstar had this table, didn't it? Where we had the suffixes across the top. And we have prefixes down the side of the in signals. So we sliced them up into a prefix and a suffix, and we put the outputs in the table entries here. And what you observe, for example, when you add a new suffix to fix an inconsistency problem in the table, is you have an entire column of empty entries there, and they all have to be filled in. And they're all independent of one another, so why not just do the whole lot concurrently, right? So there's if whichever automata learning algorithm you look at, there are always a lot of computations that you can do in parallel. And indeed, as I think I pointed out before, the bottleneck is typically the latency of the system under test itself, okay? So by cloning lots of copies of the system under test and doing all these jobs in parallel, you can really, that's the best way we know right now to overcome the latency problem. So you can sort of restructure the algorithm. This is a slightly more detailed picture to show you the fact that you create multiple copies of the system under test, and these things sit out in the world like servers, okay, and they just serve queries and send back the results. And the communication layers around here, they just manage, you know, marshalling the data so it comes from a place and it goes back to the right place. So apart from the you know, running this on the system under test, many copies on a multi-core machine, the rest of the architecture is basically the same. Of course, the learning algorithms here have to be multi-threaded, okay? So there's some work to be done there. Right, so here is the scenario. This is one of, I think, 6 use cases in the SafeCop project that we're studying, and probably very many people in the room know this. So a platoon, mainly people talk about heavy goods vehicles for platooning. You could have private vehicles, but the business case is not so strong. The business case here is basically that when trucks create a hell of a lot of slipstream and turbulence, and if you can position it right, this vehicle here, if it's fairly close to that one, we can avoid the turbulence. So it can be aerodynamically very advantageous to bring these things close together. Of course, so you save fuel, right? But of course at the expense of the inherent safety. So the closer that you are, the more chance that things could go wrong, particularly in an emergency, like in an emergency brake, okay? So we can discuss about what's the optimal distance here. There are at least two different protocols for platoons. One is fixed distance, which I think is commercially the one that one sees more commonly. We, for just other internal reasons, we looked at fixed time headway. So the time headway is if you freeze this picture at any time, you look at the velocity of this vehicle here, how much time would it take for this vehicle at its current velocity to catch up to that position? Okay, that's the time headway. So you can have fixed time headway, and you can see it in the vehicle. It's typically set to somewhere between 1 and 2.5 seconds. And there you actually have a chance to set your own comfort zone or your risk tolerance zone. So if somebody like me would go for like 5 seconds, right? I wouldn't trust it at all. The more you know about automotive software, the less comfortable you get. So that you could say is fixed risk as opposed to fixed distance. Okay, I think these are the two main alternatives. And then the whole point is it's sometimes called an electronic tow bar. So there is software that, based on the distances between these adjacent vehicles and the velocities that they're traveling at, modulates the gas or the brake in all follower vehicles so that they respect either the time headway or the distance headway to the vehicle in front. So it's called longitudinal control. You probably know the algorithms quite well. They're refinements of ACC. Here we're going to use, in this particular simulator, we're going to use CACC, cooperative ACC, which is a wireless approach. So either you could use the radar to detect the distance with the noise issues that involves, or you could use the wireless with a GPS sensor. So each vehicle can just relay its distance or its position to the follower vehicle. Of course, that's also subject to noise, but it's a different kind of noise problem, okay? And presumably more amenable. So I must add, I'm not a comms person at all, so I'm sure Elizabeth is going to jump in from time to time and correct me. I'll rely on you if I say something stupid. So the whole of the project is working with a specific protocol, which is the 802.11p protocol, about which I know next to nothing, other than that we have a fairly accurate model of that in the simulator that we've built. There are many, many different proposals for CACC algorithms. They've been around for quite a number of years. And one of the things you can do with this tool is benchmark them. And you can benchmark them in terms of safety. If you fine-tune the system, of course, what you want to do, a natural thing would be to bring the vehicles as close together as possible such that they never ever crash under any circumstances. What does under any circumstances mean? There's a hell of a lot of parameters there, right? But we can systematically work through these with machine learning. Machine learning, as I hope you recognized yesterday, is nothing other than a very, very systematic way to explore a state space. And systematic because it's like having a map. If you were to explore the city of Halmstad without a map, you'd get lost no end of times, right? It would take you a long time to get around the whole city. But if you have a map and you can tick off where you've been, you don't have to go back there. And it's the same in machine learning. Machine learning gives you the ability to say, this is definitely a new state. And from this state, I at least want to know what are the next state transitions, okay? So it's highly systematic. I was talking yesterday about stochastic equivalence checking, which is necessary at some times, okay? There are certain points where all heuristics fail, and you've got to do something else. You could ask, well, how many is that? It's typically much less than 1%, even less than 0.1%. So there's very, very little randomness in this state space search. Yet, if you tried to build an automata with a random sequence of strings, it would be incredibly wasteful. I invite you to think about this, offline. How long it would take you to build a certain automaton model just with a random set of strings, okay? And think about the scalability of that. A random choice of strings is basically the same as passive learning. Think that through. And passive learning, as we saw yesterday, is NP hard, right? So there's a hell of a difference. So there are many different CACC algorithms. It turns out that some perform better than others from a safety perspective, and I'm going to show how we analyze that today. I think the main thing is that we want to study this trade-off between safety, so you get less safe as you come close together, but you save more fuel as you come together. So where is this crossover point where you're saving the maximum fuel you can, but you're still safe? Now that's going to depend on a heck of a lot of parameters. It's going to depend on very much on the different performances of these trucks. And this can be a non-homogeneous platoon in general. So this can be a Scania truck, this can be a Volvo truck. Or with, this one has worn tires, this one has good tires. So the number of variables is vast. One cannot really deal with the entire situation in full accuracy, but with some simplifications you can get at numerical answers. And I would say these numerical answers are difficult to get at any other way. So we're going to look also at a quantitative approach to safety analysis, okay? In other words, pulling out a number which says this is the safety threshold, and when you step over this number, you are not safe anymore. And here's the reason why. So the simulator is quite streamlined. Nowadays we're also moving to more complex, physically complex simulators. You'll see some results later on. So basically there's a brake-by-wire system here. These are ABS units out on. This is a four-wheel vehicle model. And there's a global brake controller that takes the manual signals only from the lead driver. So these are switched out for the following vehicles, which instead generate their brake in their their brake in their gas values by applying an ACC algorithm. Here we just use PID algorithms. The state of the art is, of course, model predictive control, but we've not yet found anyone who will give us a model predictive controller. If you have one, we're very interested. But already if you look at different PID algorithms, you can see what's going on. There are different behaviors here. And then this is the sort of the wireless component. So odometry is through basically GPS modeling, and then we need to be able to communicate with the other vehicles. And we also have, on top of the vehicle model, we have a comms model. So there's a block inside each vehicle that sort of shares the bandwidth between, on the one hand, the GPS to relay the position and velocity, and on the other hand, the emergency brake protocol, which also is a protocol extended over time. And then that goes over a radio channel. My colleague Karl Bergenham has been very interested in noise modeling here, so that we've been building more and more accurate noise models based on, he has some empirical measurements for platoons. So he has measurements of packet loss, both on the, he has what was it called, MIMO, is it multiple input, multiple output solution? So a left and a right hand side antenna, which for reasons unknown to me, give different values of packet loss. And he has measurements in different geographic regions. And then I think we simply did a least squares fit of a linear model to these things to get a general model of packet loss there. Right now he's studying models of the burstiness that one can see in the data. So it's a multi-hop communication model between the vehicles. That's the main comms model that we've looked at. So what is the main number one thing that you want to study here? You want to know that platoons don't crash. You want to model that in linear temporal logic, which is where we always fall back on for modeling. And it's a pretty simple equation or formula. between the ith and the ith vehicle in the platoon, there's a gap. And you can observe this gap at different times. And of course, this gap will expand and contract, partly because in fixed time headway, it's velocity dependent anyway, okay? So the gap will grow as everyone speeds up, and it will contract when they slow down. But of course, the control algorithms are imperfect anyway, so they will over and undercompensate. So there will be a kind of a swaying motion going on around a vehicle. So that there's quite a complex dynamics in that distance value over time. And we're going to visualize that later on. When we do learning-based testing, of course, it looks for counterexamples to a formula such as this. So, after some time in a test sequence, which is a sequence of gas and brake signals to the lead vehicle, which bring the whole platoon into motion. And then after some time, allegedly there is a crash. That's with at least one pair of vehicles. That's what the model checker is trained to look for. But you typically find that the reasons why you got into that crash kind of happened much earlier. And this, I think, is a traditional phenomena in testing. In testing, you're looking at observed behavior. But the reason why code goes wrong is often for internal reasons. So something goes wrong internally, but it doesn't manifest until a long time later. Okay, this is something that we have. You probably know this from your own coding experience, but it's a very well known phenomena in testing. So we run LB test on this linear platoon simulator. We stimulate the lead driver here. What we have to do is quite a bit of time discretization to make this thing work in practice. The simulator itself runs on a 1 millisecond cycle. So you need a very short cycle to get accurate behavior of the control algorithms, okay? Otherwise your numerics just go wrong. But there's no way that you can string 10 or 20 millisecond cycles together and get any interesting kind of use case. So you have to block together many, many thousands. How many? One has to check this empirically, and I would say that it depends a little bit on the length of the use case that you're trying to analyze. So here in this kind of work, we always have the feeling that a truck platoon has infinitely many possible behaviors and infinitely many possible situations. So the only way you can manage that sort of methodologically is you pick out the use cases. So for a platoon, there would be use cases like, high-speed cruising on a straight piece of motorway. There would be joining the platoon, leaving the platoon, changing lanes, a vehicle entering in between two platoon vehicles and so on. So you have to sort of take the continuous world and sort of pull out stereotypical situations of reasonably short time length and analyze those, okay? So this is the kind of work that we do. So I'm going to show you the results for the very first use case, which is just high-speed cruising. So high-speed cruising is something that you can achieve already in a minute. You'll get up to the legal speed limit for most countries, and then you can carry on a bit longer. And then basically the world is going to just repeat itself after that, okay? There's nothing really substantially new going to happen. So that you can hope to make a finite state machine model of high-speed cruising if you quantize the time enough. We use 5-second cycles. So we bunch together a whole bunch of 1 millisecond steps until we get 5 seconds of driving. Or said differently, every time we modulate the lead driver's behavior, we wait 5 seconds and then we change the value, okay? So when we might gas 10% for 5 seconds, then 30% for another 5 seconds, then we might mildly brake, then we might gas hard for another 5 seconds, and so on. And in fact, any combination of the signals is allowed because it's physically possible, okay? There are no controls on the pedals. So it's a very open user interface. Of course, if things are done by wire, that would change. So let's look at the earliest use case we studied was high-speed cruising. and we studied it for different platoon sizes. We hit this limit here because a hashing algorithm that we were using kind of blew up, and I still haven't had time to fix it, but one could fix it, and there's no 6 vehicles is no inherent limit. And the initial story you wanted to know is, look, how scalable is this technology? Where do we blow up? Because most tools blow up eventually, don't they? Where do we blow up, and also why? So this is running a multi-core, a multi-threaded learner on just a 4-core machine. This is work done about 1.5 years ago. We can see we've graphed for platoons of different sizes. So basically the sizes go up, okay? Where do we start here? Is it 2, 3, 4, 5, and there's 6 up there. So notice that the initial model that we get for a 6-vehicle platoon, the smallest initial model is already about 55,000 states, okay? And it takes off from there. So what's nice about these curves is that, they're neither exponentially blowing up that way nor dying out that way, okay? So you can see that we're making steady progress, at least in terms of state space size, okay? These are hours of course, we're talking about big data sets here, so they do take hours to run. What's also nice is that there's more or less a constant increase in the gaps, so it's not like the analysis is blowing up in the number of vehicles in the platoon. And down here, just for cross-reference, you can see that this is a purely sequential learning algorithm run on 3 vehicles. I think what's also a little bit striking is that you can actually see that the gradient on the 6-vehicle platoon is higher than the gradient on the 2-vehicle platoon. It's simply growing faster. So one does sometimes see a lot of unusual phenomena that you wouldn't have expected to see. This is done, as I say, about 1.5 years ago. We're constantly working to optimize our tools. If I take this data point out here, I think it's on the next slide. So the biggest data point that we had, it's almost a day of work. It's about 21 hours, is it? It's nearly 65,000 states. It's 1.35 million transitions because it's a 21 input alphabet. There are 10 possible gas values. So I've discretized on a 10% input for the gas, and 10 brake signals because I discretized 10% intervals there. Your foot probably couldn't distinguish 10% change. You couldn't get 10% exactly right on your foot. So I think it's a fair approximation of how one would actually modulate a brake or a gas pedal. So you can certainly max gas and max brake, okay? So these are quite big models. They killed new SMV, which was our model checker, but we hacked a pretty primitive explicit state space model checker and got results out for this model in half a minute. So it's not actually an inherently difficult formula that we're trying to solve. It's just that the codings used in USMV sort of screw everything up, okay? So this did 1.5 million test cases. A test case here, I think, was on average, about 14.5 steps, okay, where a step is 5 seconds of virtual time. So that gives you, I don't know how many, I can't do the math off the top of my head. It's in a paper, you can look it up. If you sum all the steps in virtual time, you get to about 2.5 years of virtual driving, okay? If we repeated this experiment today this is on a 4-core machine. If we did this today on a 28-core machine, we'd get to about 9 years of virtual driving, okay? That can be done in 18 hours. So you can get very extensive searches of the state space through virtualization, through concurrency, and multi-threading the algorithms. And as I said, it's my opinion that these are much more systematic than a randomized approach. Okay. We found errors which were very difficult to find in this situation here. So there's a state which is labeled with too close, because it's the calculation of what the distances are over all vehicles, right, at that time. And this was found in just 101 states of those 65,000. So percentage-wise, it's this. Is this a risk value? I would say not. I would say the probability of hitting those states, well, first of all, it would depend where they lie in the state space, okay? And I don't know where they lie because the state space is too damn big to even visualize, okay? They're not in the first state, I can tell you that much. But if you wanted to do a sort of a risk modeling, which you can do, I think the correct thing, risk is a very tricky problem here, and yet it's a problem that we're asked to comment on in the SafeCop project. And it seems to me that the correct approach to risk is a sort of sum over all paths of the risk, of the probability of going down that path in the state space. So drivers don't commonly modulate between max brake and max gas and max brake and max gas, okay, unless you're sort of psychotic or something, right? So that would have it's technically possible, but is extremely low. Compared to what? Compared to a driver model. So in the industry, people have driver models. There's a different driver model for, you know, the teenage driver that's just got their license, to the little old lady who has trouble seeing, or the little old man, I'm getting there with my vision, who, you know, is super cautious. And then there's the professional driver, which would have a different driver model. So it's known in the industry that there are different driver models, okay? And these are basically, you can think of these as sort of Markov models of the likelihood of taking certain steps. So you can plug such a Markov model in to the learned automata, and you can sum over all paths. And you can get the true probability, at least from that perspective. There are other probabilistic aspects around, like packet loss and so on, okay? So it's a multi-factor. Risk is really a very highly multi-factor problem here. But at least for certain, you know, if you have a model for that factor, you can bring it in. So plugging a driver model in, we could work out what the true probabilities were of being too close, okay? So that was high-speed cruising. Let's look at emergency brake. In emergency brake, the key idea here, and this is not my algorithm design, so I don't want to say it's good or bad. It was a proposal that we had from Camcom that vehicles can't brake better than their braking capacity, which varies according to, you know, the quality of the tires, the quality of the brake discs, the technology for braking, which is not only brake discs and so on. So that every vehicle will have a different sort of braking capacity in a platoon. And you want vehicles to be able to max out their braking capacity, okay? And if we maxed out here at the front, this person behind could not achieve our that braking capacity, they'd probably hit us, okay? So potentially a safe way to go is to sort of max out from the back, okay? So the last driver maxes. This is the intuition behind the algorithm. Whether it works or not is another question. But the intuition is that you allow the later vehicles to max out their braking capacity, okay? And that will not sort of impact on the vehicles in front. So then this signaling has to be done wirelessly, and you have to worry about, you know, dropped packets and so on. I don't want you to read this slide. It just gives you a sense of the complexity of the e-brake protocol, okay? These things are either published or submitted for publication, so that within a few weeks' time you should have public access to most of this stuff. And you'll get my slides in any case. So what Camcom wanted to know was, does this actually improve braking, okay? Well, you actually improve if there are certain braking values, just using CACC, like, you know, minimum stopping distance, and you reduce that by using e-brake. So if you didn't reduce that one, or some other important parameter, like people not hitting each other or bringing trucks closer, So there are certain, more than one numerical parameter that if you didn't improve on it, you wouldn't buy this algorithm, right? It's a waste of time. So Camcom wanted to use our tool to find out actually numbers that preserve safety but even improve on it. Okay, so those are numerical values at the end of the day. So we started doing this in SafeCop, what we call quantitative safety analysis. So previously, when we looked on Monday, things like, dual control steering, well, somebody gives you a requirement and it's just pass, fail, okay? And if it's fail, fix it. And keep fixing it until it stops failing, okay? End of story. But there are no numbers coming out of there. It's just pass, fail. So now we want to do quantitative safety analysis. So typically it's an optimization problem. We want to find, there are certain system parameters, for example, time headway, and we can tune these parameters, so we'd want to bring time headway down to improve something else. So what's the maximum degree you can tune this parameter without compromising safety? So some of them are maximum values, some of them are minimum values, doesn't actually matter which it is. The main thing that you want to know is that the value varies monotonically in terms of the behavior of the system. I'll perhaps come back to that in a second. But mostly they do, because nature tends to be continuous, so oftentimes it tends to be monotonic. So for example, we can look at the time headway between vehicles, and we know that if you respect this time headway, you'll always be safe, according to our massive simulations. But if you bring in e-brake, well, you'd like to actually allow yourself to bring the vehicles even closer, okay? Because the very unusual times when sort of chaos breaks out, an algorithm manages the chaos, which it was not doing before, okay? So that could be one hypothesis, that you buy this e-brake algorithm and you can save fuel, because you can run the trucks together more closely, okay? So how do we do that? So you can take these environment parameters and you can just perturb them from one test session to the next. So what we actually do is we take a good old-fashioned bisection method. We find, for example, a very high value of the parameter where the safety formula is always true, so the system is very obviously safe. So take a time headway of maybe 5 or 10 seconds. There'll be no problems there, right? And we take a second, that's the upper bound. We take a lower bound where things are obviously unsafe. So let's take 0.1 seconds, okay? You'll definitely crash with such a short headway. And then we're going to squeeze that interval. So we squeeze the interval by bisecting it, and then we run the simulator with the parameter set to the bisection value, okay? And we look for failures of safety. So we'll do a long search. So this may be, of the order of tens of hours. We'll do a massive search, and we'll come up with an answer. Of course, this is not an exhaustive answer, but it's probably a good approximation to the truth. And what else would you do if you didn't use this way? Probably Monte Carlo, in my opinion. But what did we just say about Monte Carlo? It's not so systematic for mapping out the state space, okay? So already we tried this approach very early on because we just looked at different ACC algorithms and we said, look, what's their characteristic value? Is one more powerful than the other? Does one save more fuel than the other? It does indeed. These are two published algorithms in the literature. There's a heck of a difference in their safe time headways, okay? The boundary. So you can get twice as close on a time headway on the second algorithm. So you'll see this in general, okay? You can design a new control algorithm and you can ask what's its performance vis-a-vis safety in 5 minutes. And you'll just get different results, okay? So I'll skip forward because I think you've understood many of the points and I'm running out of time. Now I've got some nice film clips to finish off on. Everyone likes film clips, including speakers, because we don't have to do so much. This is material that we've just sent for publication now. We wanted to characterize the combination of high-speed cruising plus emergency brake plus 2 different models of packet loss, none at all, and a model. I think this model is based on the E4 motorway, okay, for whatever that's worth. It's an empirically inferred model. And we wanted to show that when you get packet loss, well, of course, if you get packet loss, you need to allow a slightly longer gap between the vehicles, okay, to preserve safety. But how much? Okay, that's quite hard to answer. And what's that sensitive to? Well, we played around with, for example, the number of vehicles in the platoon. That's quite an interesting question. And we graphed out the results. So this graph here, this is the threshold between safety above the curve and unsafety somewhere below the curve. If you ask me where, I'd have to go to the counterexamples and we'd sit down and study them, okay? But somewhere here, there are counterexamples to safety. Of course, you can't, these are discrete points. There's no such thing as 3.5 trucks in a platoon, but you understand what I mean, okay? So notice that there is a significant gap. And intuitively, I think you would expect that, you'd have a row of curves going up like that as you get more and more packet loss. Notice that the time headway kind of plateaus out, so that in terms of, scaling up the platoon size, you don't scale up the time headway according to the platoon size, not according to this data at least. So that's a kind of analysis that we can do. Let me finish off the talk and the course by showing you some film clips. As I said, when you produce these counterexamples, so failures of safety, it's very interesting to see and try to understand, how did you get into this bad situation? What went wrong? So here is a counterexample to, or a failed test case, you could call it. So it's a sequence of, these are quite high gas and brake values. What's interesting, I'm going to show you this film clip, but I'll explain it to you before. So we've got 6 vehicles here. These are the inter-vehicle distances, the velocities of the individual vehicles, and the acceleration values. The acceleration values are the interesting things to watch here. This PID algorithm will introduce the idea of a compression wave. And you have a compression wave in a platoon where some vehicles are accelerating while others are decelerating, okay? So that sort of pinch, if I can call it that, in the platoon will actually travel along the platoon, okay? We know this from our own personal driving on the motorway. There are ways to get that pinch out, but not this way there aren't. So we set in motion a wave, and then you could say at a very unfortunate moment, actually when the wave is about to crash on the final vehicle, remember, what does the final vehicle do? It's the first vehicle to brake in an emergency brake, isn't it? So just as the wave is about to crash on the final vehicle, we ask it to emergency brake. And let's see what goes wrong here. Green means a vehicle is respecting its design parameters. Okay, so some of these vehicles will go yellow. I think this will be the first one to go yellow. Give it a bit of time. We probably need to brake before we get anywhere. So this is the currently executing lead vehicle command, okay? Oh, these are not inter-vehicle distances. No, these are absolute locations. I take that back. There, this is going yellow. That means it's just breaking its design parameters for the distance with respect to the velocity. That's not, fatal, but it's a bit disturbing, shall we say. So now this compression wave is traveling along here. We've hit the e-brake command, and this driver was too close anyway and could not pull out. Okay? So this is kind of interesting because it's a failure of an integration test. It's an integration of 2 use cases, either of which would actually work okay on its own, but when you put them together, there are unfortunate interactions between them. And I would suggest that this is something that's quite difficult to analyze other than sort of empirically, I feel, personally, at the moment. Let me show you another film. That's an HTML simulator. I see Vahid standing up there, so I realize I'm running out of time. Let me show you a last film. This is something that we've done in a professional simulator called Truckmaker. It's basically a similar scenario. except that the physics of this vehicle is now much more accurately modeled. So this is extremely detailed physical modeling here, much better than we could ever devote the time to or have the knowledge to know how to do. This is a 3-vehicle simulator. This is Brutto, the famous high street supermarket. This is a mother and child here, and notice a football. So guess what's going to happen? I'll let the film finish, and then I will comment on it. So all hell breaks out. But no one dies on this occasion. What's important to understand about this film versus the previous one, oh look, this must be the police car coming in here to find out what the hell happened. Whoops, we lost the film. I should have frozen it, I guess. Let's watch it again, it's kind of fun, I think. This time I will comment on it. What's interesting to observe about this film is that you can not only send in lead vehicle signals from the active learner, you can also send in signals to the environment. We've used this in fault injection testing, where we actually use the learner to inject at times things like bit flip errors, okay, dynamically. So this bit flip happens at some point in time, and we've used that to analyze the consequences, the reliability of the hardware, and then the software on top, and so on. Just as you can inject a bit flip error into a simulation, you can inject a football or a child or a mother into a situation. They're just values, abstract values, okay? So that what we're moving towards now, let me get my concluding slide back. Where's that gone? Here we are. I had some other films, but we did some work in Unity, but you can ask me offline about that if you're interested. So some conclusions then just from today's talk. We can find quite rare errors. How scarce they are has to be relative to a probability model. We can certainly reverse big models. We're not frightened of that as long as we have multi-core machines, which is the main way to handle the system latency, which is the biggest problem actually very oftentimes in the real world of practical case studies. So of course you can always have more cores, but how do you deploy them? It's not always so obvious. We are moving into 2D work now, away from the original 1D simulator. And when you get into 2D work, you want to add space to time, and that's about the cutting edge of our work now, which is looking at spatiotemporal logics to model use cases like the child running out into the road or the vehicle pulling in between two platoon vehicles, okay? So these are things that happen in space and in time, for which the very first thing is you need to be able to express them, okay? You need to be able to write them in a formal way. So we have a paper that's submitted to conference right now, and hopefully that will come out, and perhaps the next time I come by here I will have the chance to talk about that.
Sounds great.
Thank you.
Thank you very much, Karl. We have time for maybe 1 or 2 questions. Yes?
Could you go back to the Packard graph?
Yes, yes. I'm not the author of this. I can only sort of present it to you without comment. I think it's the average number of successful packets, probably on a sliding window. Where are we? Sorry. Is this?
Headway versus...
Oh, right, yes. Yes, now I know what you mean, I'm sorry.
Yes.
So this figure here, so this is perfect communication, the lower line, and this is communication against, so we did a linear regression on this data set, okay? Specifically this data set here. So we do it because this is only, I think, three followers and 1 lead vehicle. Okay, so there's a 4-vehicle platoon. So we try linear regression to know about, for say, a 6-vehicle platoon.
So Packard loss rate is like 3%?
It varies. So this is packet loss rate measured locally at the different vehicles, right? So packet loss at the third follower out here is much higher than the immediate follower, number 1 there, okay? So you can see that there's an increasing curve, which is perhaps intuitively what you would expect. I don't know why it's not. These are the left and right antennas, I think. Sorry, this is the right communication, that's left communication. I don't know why they're asymmetric, but those were the measurements. These were measurements done in a project called RELCOM by Karl Bergenham, and there's a publication where you can look at it. Actually, I asked him to talk to you, but he's not. He works in Gothenburg, so I don't think he could come back today. But if I give him your email number, you can. I think there are a lot of interesting phenomena in here. So he's studying the burstiness phenomena quite a lot right now.
Other questions? Yes.
There was this competition a couple of years ago where students and others were trying to make real cars in a platoon. And one of the error conditions there was that when a car went into a tunnel, their GPS signal was lost, and then they continuously transmitted the same position. So it meant that all the other vehicles saw it as standing still. Could you actually model that and simulate that?
Oh yeah.
But would you need to then invent this problem beforehand? So
You'd have to. So what you perhaps grasped with the last film there is that besides, where's it gone? You know, besides designing the platoon simulator, you can also design the environment. I don't know why I've lost my film there. No, was it VLC we were using? Yeah, there it is. So besides, is it running? Yes, it is running. Besides designing, you know, the control algorithms internally for the vehicle, we also design the roadway, you know, the geography in general. We can, in our own simulator, we can also set the packet loss rates to different mean values in different parts of the geography. So we could design a tunnel, we could reset the packet loss rate inside the tunnel. In fact, it just has to be a virtual tunnel, okay?
yeah,
So
but
you
the problem
set
is
it, yeah.
that the algorithm for transmitting the positions was incorrect.
Yeah, I understand, yes. Yes.
So
So unless there's some redundancy in the situation that observes that and steps in, things will go wrong, of course. It will look static. And if it looks static, it will probably look actually a little bit like an emergency brake. But the protocol won't be activated, so instead the CACC algorithms will just observe. Well, will they observe? They've lost GPS. If they had radar, they could still observe that the vehicle in front was not moving. Otherwise, that's the end, right?
the good thing is that the vehicle was actually moving, but the cars behind was needing to brake.
Yeah.
Because
Right.
they sensed that the vehicle was stopped.
Yeah. It's a complex scenario. The simple answer is if you build in all these factors into the simulator, yes.
Yeah,
So if
but the question is how to have this algorithm for the GPS receiver and the sort of connection to the 11P protocol for transmitting the positions. There was an error, a mistake done. So then you need to include that code in your simulations to be able to detect
whatever you can build physically in the real world, okay, you can just execute that inside a simulator. That's the shortest answer.
Yeah. But then you need to have all the components, all the ECUs, the hundreds ECUs, more or less, in your simulation.
Or at
What's
least
tricky is the
model.
environmental modeling, right? But of course, professional tools have a lot of environmental modeling, right? I won't say it's complete and fully accurate, but there are many, many factors there.
It sounds like we've started on this really interesting thread of, you know, modeling and its impact on the results and so on. And this is a very good segue to lunch and the topic
Yes,
for
the
the
environment's
lunch
really
discussion.
useful
That's right,
sometimes.
exactly. So
It
thank you
feeds you.
again very much, Karl.
Thanks.